Hi, I'm Liz. I'm a first year PhD student in astronomy, and today is going to be a paper that's not really that close to what I do, but it's kind of as an exam for my one of the courses that I took this semester. I have to present a paper, and I thought, well, since I have prepared the presentation anyway, why not turn it into a paper review for the channel? So, okay. So, and in the context of the review, I thought it might be useful to introduce the concept of microlensing first. So microlensing is a relativistic effect that is of some massive object changing the path of the light from some background source. So, and there is a little schematic here where the background source in this case is quasar, the lens is the galaxy, and typically the light from the quasar, it goes into all directions, including here, but because there is a galaxy, it has a significant mass, it warps space-time, and it changes the path of the light, redirecting it onto the Earth, and we see it as the additional image here in on the angle, at the angle different from the angle of the source. So here in this picture, the angle onto the source would be theta 0, and onto the image is theta, they're different. So there is, as relativity theory is a very developed theory, there's all these formulas and everything, the whole theory is about microlensing is very fleshed out, and we know how these events should look, and they're applicable to not only very massive bodies, but also just all macroscopic bodies, including those that we can't see. And in the context of exoplanets, that has been proposed as a method to search for rogue planets or planets at the huge separation from the star. And this is like the main strength of this method, that essentially I think it's the only method that allows to detect planets that are not bound to any star, because other methods are kind of very reliant upon planets either orbiting a star or what else? Like shadowing the star and so on and so forth. Like in all other methods, you need the star as the kind of as the central point, whilst that you measure stuff against. Whilst in this case, the planet itself, well, except for direct imaging, yeah. But okay, the direct imaging, you can see the planet itself there, but I think it's not really used to detect rogue planets. It's kind of quite difficult, like where do you look? Anyway, so yeah, this is a very unique tool built for like finding planets that are not bound to stars or at huge separation from the stars. The only offset is that, well, maybe not the only, but the major offset is that it's kind of a unique case, and you need you can detect it only once. There's no periodicity, no anything. It just passes once, creates this event, and that's it. And you need to kind of really look for it and be really careful about identifying it and catching it, because this is a rare event. In like a particular microlensing event is one of a kind and cannot happen ever again. It's just it happened. What's also important here on this slide is this theta E, which is called Einstein radius, and this is basically a measure of like how to what distance the light from the source would be distorted, given that the source and the lens are on the same line of sight. So here on the image that is not, but still, if they would be, how would to what distance the light would be distorted to? And even when this is not the situation, it still can be used as a measure of how the angular shift of the image. And it's useful because if you can identify that value, it holds information about the lens itself, including its mass. So you could, in theory, it also depends on the distance between the relative distances. So it's not a direct weight to mass. You also need to know this stuff, and I guess L2 and L1 are the most sensitive, because like you can measure L probably if you see. I mean, you for the microlensing event, you need to see the baseline. You can get L from whatever method, but if you don't see a lens, like in the case of a planet, you can't get L1, and you definitely can't get L2 because all you have is a projection. I mean, there might be methods, but it's very complicated, much more complicated than just straight L, because you don't directly see the thing. Yeah, but it is somewhat a measure of a mass of the object. So yeah, and so to tackle this problem and find planets this way, several surveys were created that were the goal of which was just to target a very star-dense regions of the sky and just go through it, monitor them, just to see if there's some kind of amplification that is looks a lot like what the relativity theory predicts the light curve magnification would be, the intensity magnification would be. And one of those surveys is Ogley survey. There's also another one, maybe also a bit more of them, but in the context of this paper there's two surveys that are a part of this particular microlensing event. Okay, so this is the name of the object. It is in the galactic bulge. The star, the baseline that they looked at, that is essentially what it was magnified, the source, is known to be a bright giant with the magnitude in I band, this one, and the color index, this color index equal to this. So first this event was identified by this Ogley survey in 2019. Then 2 days later it was independently identified by another survey, another network called KMT. Ogley survey was observing this with only 1.3 meter telescope in Chile. KMT observed it also by 3 telescopes, one in Australia, one in Chile, one in South Africa, all of them identical 1.6 meter telescopes. All observations were mainly done in I band, some supplemental were in V band, so we could get a color index as well. And so there is a total of 4 sets of data, 4 sets of 4 light curves for this object, for this baseline. So here it is. There is the light curve of all 4 telescopes, and also what you can see here is the results of the single lens model. So again, the theory when it comes to relativity theory, all is pretty much fleshed out, and we have a really good idea of how it all should look like, and there are fitting models ready to take on these events. And that's what they do here. They start with a single lens model and fit it to the light curve, to I think all of the light curves separately and maybe combined. I think they mostly did separately and then kind of averaged it or something. It doesn't really matter. I mean, it might matter in the details, but you know, whatever. The idea is the same. And on the right there are these fitting parameters. So obviously T0 is the moment of the peak, basically when the separation, projected separation of a lens and source are the smallest. Then we have the duration, show the renormalized duration of the event. Then U0 is the separation, the minimal separation of those two. Then the rho is the angular size of the source in Einstein radiuses. Then IS is the baseline magnitude. Fs is the blending fraction. So the thing is, when you deal with a high star density environment with not a very high resolution on your telescope, you might get the situation when your source star blends with some other stars, and only a portion of the baseline that you have is magnified, and then kind of it affects what would be the rho value in this case. And you can see that there is 2 columns here, one of which, when they took the blending fraction as a free parameter, that they fitted as well. And another one is when they did some blend prior, in form of that they took a Hubble image of the same field and looked at how, and kind of cross-referenced star, and looked at the cross-referenced stars on their image and Hubble image, and compared the fluxes from those stars to see if there is a significant difference. And it turned out that there is not, and this is their prior, that essentially there is no blending in their case. They're kind of, well, in a way, lucky. And you can see that this kind of affects the rho, which actually this rho defines the magnitude of the event. So it kind of written here just as simply, I introduce it as simply as a angular radius of the source renormalized, but it really is what defines this the magnitude of the event. And so it kind of is affected by a factor of 2 just from these different blending fractions. And the rest is not really comes from fitting themselves, it's more like to assist fitting, and I will talk about this a bit later. So overall they get, as you can see, a very nice fit, and and these are kind of the values with the blending prior of 1, essentially no blending prior. That all of your flux comes from the source and no background, non-amplified flux there is. Okay, good. But then they also had to think about a possibility that what if it's not a single lens? What if there is a binary lens just in a huge separation? Which also can be a possibility. And they tried, fitting that model. Of course, new parameters were introduced, like mass fractions between the components, the separation and stuff. But overall, they and that can kind of give you information if it's a better fit about what kind of components there are, how their masses correspond to each other and stuff. And so they tried fitting that, and what they got is that they did get a better fit overall because of this bump. And you can see that in the data that it seems like there is indeed some kind of bump in the data. And when they compare the he squared here of single minus binary, they get that in this around this bump there is a much better fit by the binary than by the single lens model. So at first it started looking like, might be a binary might describe it better. But then they looked at another two things. So first of all, as you can see here, and there are different lines for different data sets, so they kind of were fitting separately, the data sets separately. You can see that in the early, that the event itself and some point, and especially some point after it, there is a dip. So for some data sets, single describes them better, even during the event itself, not after it. So like for orange and blue, it's even better. And then there is a dip in quality, where basically single describes it better. And that kind of, and again, the relativity theory gives very, very exact solutions. This kind of suggests that it's a bump not of microlensing nature. And they remembered about the star, what kind of type of the star it is, and they asked themselves if there is some kind of inherent variability to the source, maybe. So they took light curves, archival light curves for that star. Here they are. And they saw that there is indeed some kind of low amplitude variability on the same time scale as here. And so 2 plus 2, there is a variability in the star, and this bump is not very well described. It's not that well described by the binary lens model. So most likely that's not really an effect created by the binary lens. Most likely it just happened to be a variability on top of or very near the microlensing event. Also, another thing that put the nail in the coffin is that the best fit mass fraction turned out to be not that big. So it would correspond to something like a Jupiter mass object being orbited by a Neptune-sized object, or maybe not Jupiter, but like a brown dwarf or something, like something very small orbited, but something not much smaller. And they said that it seems like a very unlikely combo. So these three things combined, the results of the fit, how fares with a bump and this inherent variability, they say that, okay, it's probably not the binary lens, it is a single lens, we should stick with that. No blending, single lens. Okay, so now that we've established that it is a single lens with no blending, now we can try to get some physical parameters here of the lens. So, and there are two that they want to get. So the first one is obviously Einstein radius, and the other one is the relative proper motion. But to get the Einstein ring, you need to know, and you remember from the fit we get rho from the magnitude. Then to get the Einstein ring, we need to know angular size of the source. And so for that, what they do is they have the color index and I magnitude, but it is a reddened. When they measure it all, they don't account for interstellar reddening. So they need first to get the dereddened properties, dereddened photometric properties of the star. For that, they use this method from Yo et al. 2004, where they plot this diagram, and essentially the assumption is that the difference in these coordinates between objects is not dependent on the reddening. So it's kind of preserved for dereddened and reddened objects. And for the red clump, they know the reddened value. They can measure it with their telescope. And I think it was this Oakley for kind of hints that they measured it with their, as a part of this survey. They did this diagram. So they get their values of a reddened red clump and of a reddened source, and they know the dereddened value of the red clump, and this difference is conserved, so therefore you can get through it the dereddened values. So once you've obtained these dereddened values, they identify the star as a K4 giant star with effective temperature of 4000 Kelvin, and through it, and I guess some theory from this paper, they get the value of the surface brightness of the object in that band, and then as you have the flux, you have the surface brightness, you can get the surface from there. And they get it, and they get this value of 20 micro arc second, essentially. And now that you have it, you can get the Einstein ring, and they get 4.35 micro arc second, which, as they report, is the second lowest at the time of publication. There was only one event that gave a smaller Einstein ring. And also they get relative proper motion, which, knowing the proper motion of the source, you can kind of assume where you can draw a region where the proper motion of the lens may lie, and they see that essentially the proper motion of the lens is quite consistent with either the bulge or the disc. It can be either of those. Can be moving with either of those. Okay. So this is what they get. In conclusions, so the observed event can be well described by a single lens. Although you never can really, you can never really be too sure, because it can be just a very huge separation of the star, of the host and the planet, or it's more unlikely that if the mass is small, it's unlikely that it's two planets orbiting each other. It's not a very likely configuration. But if there is a star like very quite well separated, then you cannot like really rule it out completely at the moment. So they say that it's most likely, I mean, we see that it's just described well by single lens. It can be a rogue planet, it can be a well-separated host and the planet. And the time scale and Einstein radius that they find are way smaller than they would typically get for stellar mass lenses. And they have this formula here that allows you to get the mass depending on the relative separation of the relative distance between the source and the lens. And of course we don't know that, but you know, given that it is in our galaxy, we can have somewhat estimates of what it is. And depending on this distance, it can be either from a sub-Neptune mass planet to the Saturn mass planet, which is either way some kind of gas giant. So overall, this microlensing event, successfully allowed to identify maybe a rogue gas giant or a gas giant at a huge separation from the star that is yet to be discovered. Yeah, I think that's it. Thank you for listening, and goodbye.